Hello everyone, I am Shivanand Upadhyay and I welcome you all on our channel Chemistry Academy for IT, JEE and NEET. This is our first lecture of physical chemistry in English and I am going to discuss a very simple topic, compressibility factor. There are 5 ways to represent compressibility factor. Today we'll try to cover all. So let us start. The first way to represent compressibility factor. When we are writing compressibility factor, basically we are comparing a real gas and ideal gas under identical conditions. So the first way to represent compressibility factor is volume of real gas upon volume of ideal gas. So in the numerator we are writing volume of real gas, in the denominator there is volume of ideal gas, and we are comparing the volume of real gas with respect to ideal gas under the same condition of number of moles, temperature and pressure. So we can feel this. Suppose on the left hand side there is an ideal gas whose number of moles is N, temperature is T and pressure is P. We know that in ideal gas there is no interactive forces, means there is no attraction or repulsion between ideal gas molecules. While in case of real gas there may be attractive forces dominating or repulsive forces dominating depending upon the condition in which the real gas is present. So in our first case we are assuming that there is force of attraction between the real gas molecule. So we know that in case of gas the pressure is developed when the molecules are going to collide with the wall of container. In case of this, when there is force of attraction, when the molecules are going to collide with wall of container, the molecules behind will attract them, they will decrease their momentum, rate of change of momentum will decrease, and finally the pressure is decreased. But we want to develop the same pressure. So in order to develop the same pressure we have to keep this real gas in a smaller container. By doing that we are increasing the number of collisions. If the volume is less, area will be less, the number of collisions is going to increase. So in order to develop the same pressure we have to keep this real gas in a smaller volume. So in the above formula, if we put the value of real gas is smaller than that of ideal gas, then we can write that the value of Z is less than 1. So in case of force of attraction, the value of Z is less than 1. Same way we can compare the other case where on the left hand side there is an ideal gas whose number of moles is N, temperature is T, pressure is P. Now we are comparing this with a real gas having same number of moles, temperature, and we want to develop the same pressure. In this particular case there is repulsion between real gas molecule, and if there is repulsion between real gas molecule, when the molecules are going to collide with the wall of the container, the molecules behind them will push them, they will increase their momentum and the pressure will increase. But we want the same pressure. In order to develop the same pressure we have to keep the real gas in a large volume. So by increasing the volume we are decreasing the pressure, or we are making the pressure equal to that of ideal gas. So in this case, in the numerator, if the volume of real gas is greater than that of ideal gas, we can say that the value of Z is greater than 1. So this is a very common way to represent compressibility factor. Most of the time we are using this formula of writing compressibility factor. So from here, if we put the value of volume of ideal gas in the above formula, that Z is equal to volume of real gas upon volume of ideal gas, by using ideal gas equation we can write that volume of ideal gas is equal to number of moles, universal gas constant, temperature upon pressure. If the number of moles of the real gas is equal to 1, then we can say that the volume of real gas is equal to the molar volume, and molar volume means there is 1 mole of real gas in the container. So we can write that Z is equal to P into Vm upon RT. Most of the time when we are using van der Waals real gas equation, we are taking 1 mole of the real gas and we are writing the value of Z in this form. Z is PVm upon RT. From this formula, now we are going to discuss the second way to represent compressibility factor. So here we have derived a formula that Z is equal to P into volume of real gas upon number of moles of real gas or ideal gas into universal gas constant into temperature of the gas. So while writing the formula, we already know that pressure, temperature and number of moles of ideal gas and real gas are same. Now from here we can write the number of moles of real gas as mass of real gas upon molar mass of real gas into universal gas constant into temperature, and in the numerator we can write that pressure into volume of real gas. And we can further simplify this mass of real gas upon volume of real gas is density of the real gas. So we can write pressure into molar mass of real gas upon density of real gas into RT. And by using ideal gas equation, PV is equal to nRT, we want to write the value of RT by P for an ideal gas. So the value of RT by P we can write is equal to this value RT by P we can write is equal to volume upon number of moles. Number of moles of ideal gas is equal to mass of ideal gas upon molar mass of ideal gas. So now from here we can say that this is equal to molar mass of ideal gas upon density of ideal gas. So if we put this value in above formula, we can write that compressibility factor Z is equal to molar mass of real gas upon molar mass of ideal gas, density of ideal gas upon density of real gas. So the value of compressibility factor can also represented in this form, which is in the form of molar mass and density of ideal and real gas. So this is the second way to represent the compressibility factor. Now we are going to discuss the third way to represent compressibility factor. Here when we are writing compressibility factor, we are writing in terms of pressure. So compressibility factor can be defined as pressure of real gas upon pressure of ideal gas. When we are comparing the pressure of real gas with pressure of ideal gas, we are comparing under the same condition of number of moles, volume and temperature. So number of moles, volume and temperature for real and ideal gas will be same. So let us try to feel this. On the left hand side there is an ideal gas whose number of moles is N, temperature is T and volume is V. On the right hand side, in the first case we are assuming that there is force of attraction between the real gas molecule. So here real gas molecules have the same volume, temperature and number of moles, but attractive forces are there. If there is force of attraction, definitely the pressure of the real gas will be less than that of ideal gas. So in the above formula, if the numerator is less than denominator, we can say that the value of Z is less than 1. So in case of force of attraction, here we can write that Z is less than 1. The same way, the second case, we are taking same number of moles, temperature and volume for real as well as ideal gas, but the real gas have repulsive forces. If the real gas have repulsive forces, then we can say we are taking the same volume and temperature and number of moles. Due to repulsion, the pressure of real gas is greater than that of ideal gas, and if the pressure of real gas is greater than that of ideal gas, we can say that Z is greater than 1. So this is the third way in which we are writing compressibility factor in terms of pressure of real gas upon pressure of ideal gas. This is also a way to represent compressibility factor. Now we are coming to the fourth way where we are writing compressibility factor in terms of number of moles. So when we are writing compressibility factor in terms of number of moles of ideal gas will be in the numerator and number of moles of real gas will be in the denominator. When we are comparing the number of moles, the pressure, volume and temperature of both the gases will be same. So under the same condition of pressure, volume and temperature, the ratio of number of moles will try to give you the relation of molecules interactive forces between the real gas, right? So here we can see that on the left hand side there is an ideal gas, on the right hand side there is a real gas, and we are assuming that there is attraction between the real gas molecule. If there is force of attraction between the real gas molecule and we want the same pressure, volume of the container is same, temperature is same. Temperature is related to momentum because temperature is related to kinetic energy. Now if the volume is same and we want to develop the same pressure, if force of attraction is there, due to force of attraction the linear momentum of gas particle is going to decrease. So but we want the same pressure. In order to develop the same pressure, we have to put more number of moles of real gas. So if we are writing that the number of moles of real gas which is in denominator is more than that of ideal gas, here we can say that the value of Z is less than 1. So in case of force of attraction, if we want to put the real gas in the same volume at the same temperature and want to develop the same pressure, we have to keep more number of real gas in order to develop the same pressure, right? Same way we can say that if there is repulsive forces between real gas molecules, so if repulsion is there, in order to develop the same pressure, we have to decrease the number of moles of real gas. If we keep the same number of moles of real gas, due to repulsion, its pressure will be more. In order to develop the same pressure, we have to decrease the number of moles of real gas, and number of moles of real gas is in denominator. So from there we can say that the value of Z is greater than 1. So here also we are writing the number of moles, and by comparing the number of moles we can say that under what condition attractive forces are dominating and repulsive forces are dominating. The fifth way to represent the compressibility factor is writing the compressibility factor in terms of temperature. So temperature of ideal gas upon temperature of real gas. When we are comparing the temperature of ideal gas with real gas under identical condition of number of moles, pressure and volume. So for both the gases, number of moles, pressure, volume is same. Now the first case, when we are saying that there is force of attraction between the real gas molecule. So if force of attraction is there, so when the molecules are going to collide with the wall of container, their momentum is going to decrease due to force of attraction. We want to increase their momentum. So in order to increase the momentum, we should increase the temperature of the real gas, because on increasing temperature, average kinetic energy is going to increase, linear momentum is going to increase. So we can say that when force of attraction is there, in order to develop the same pressure in case of real gas, the temperature of real gas should be greater than temperature of ideal gas. And from the formula, temperature of real gas is in the denominator. So if the temperature of real gas is greater than that of ideal gas, we can say that Z is less than 1. And the other case, when there is repulsion between the real gas molecule, in case of repulsion between the real gas molecule, their momentum is going to increase when they are going to collide with the wall of container. We want to decrease their momentum. In order to decrease their momentum, we have to decrease the temperature of real gas. So in this particular case, we can say that in order to develop the same pressure, we have to decrease the temperature of real gas with respect to ideal gas, and the temperature of real gas is in the denominator. So if we are decreasing the temperature of real gas, we can say that Z is greater than 1. So in all these 5 cases, Z is less than 1 is representing force of attraction, and Z is greater than 1 is representing force of repulsion. And we have learned that. I hope that this lecture is useful to you. If yes, please like and subscribe our channel, Chemistry Academy for IT, JEE and NEET. Thank you.